Fabio Pacucci, an astrophysicist from Italy, working in the US. Well, we talk about black holes, the most efficient energy source in the universe. Fabio is a PHI Fellow at Harvard University and a Clay Fellow at the Smithsonian Astrophysical Observatory. PHI stands for Black Hole Initiative. Fabio's work on black holes earned him several prizes, including the International Astronomical Union Prize, as well as the Livio Breton Prize in 2017 for his PhD thesis on the first black holes in the cosmic dark ages, which he received at the Scuola Normale Superiore di Pisa, we would say the school of Enrico Fermi. His research aims at understanding the properties of the first black holes formed in the universe. We are curious to see what awaits us in the next half hour. Welcome, Fabio. The stage is yours.
All right, everyone. Thank you for the invitation and for the presentation. It's a big pleasure for me to be here. And it's the first time I come back to Italy, actually, in more than 2 years. So you can just imagine how much I was in need of a decent coffee, at least. So today I will be talking about a very peculiar subject in this very interesting Congress. And in particular, I will be talking about what I do for my job, believe it or not, so black holes, and why they are the most efficient energy sources in the universe. So if you don't understand something, I will be very, very simple, but if you don't understand something, no worries, because we astrophysicists don't understand anything most of the times. So also if you have more curiosities later on, you can just approach me and we can talk about black holes even more. So let's start from an obvious fact. So our planet Earth, is really a beautiful place. So this is a video taken from the International Space Station, and you can see clouds, you can see oceans, continents, forests. So we have explored the universe at large, at least with our telescopes, and we have never found anything so beautiful as our planet. But there is a problem with Earth, if you can say it. So the problem is that Earth is a pretty small place. So this picture was taken around the moon and was taken by the crew of the Apollo 11, the first one that actually landed on the moon. And planet Earth is actually very small. If you can't spot it right here, it's that little blue dot there, and this picture was taken from the Cassini spacecraft around Saturn. You can see Saturn's rings over there. So our resources, of course, are limited, and there is always a problem of where to find more energy to sustain our development and our advancements as a species. And this Congress is in part dealing with these issues. So in this chart in particular, I will be describing what is the energy and that is being used in our planet and how it's related to the technological advancement of our civilization. So as you can see in that chart, the x-axis goes from the 1800 approximately to a couple of years ago, and on the vertical axis there is the energy consumption by our entire planet. This is an estimate, of course, and there is also the allocation in oil, in coal, and what else. So what matters from this chart is that as technology progresses and our civilization advances, there is always an increasing need of energy, and this is basically unstoppable, as you can see from this chart. So we can say, to some extent, that the technological advancement equals the increasing energy consumption. There is almost no way to advance technologically and to have a larger and larger population on Earth that that prevents the need of more and more technology. So in the 1960s, and now we meet one of our first characters of this presentation, a Russian astronomer named Nikolai Kardashev introduced the so-called Kardashev scale. So the Kardashev scale is a very simplistic, to some extent, way to parameterize or to describe advanced civilizations, be it us or alien civilizations, if we ever find one, on the basis of their energy consumption. So it divides civilizations in three types. So the first type, or type 1 on the Kardashev scale, is a civilization that is able to use all the energy that reaches their own planet. For example, if we were able to use all the energy that reaches our planet, for example, for our sun, then we would be, by definition, a type 1 on the Kardashev scale. A second, or type 2 civilization on Kardashev scale is able to use all the energy that is produced by their own star. So if we were able to use all the energy that our sun is producing at every second, we would be a type 2 civilization. And last but not least, a type 3 civilization is a civilization that is able to use all the energy that is produced by all stars in the galaxy that this civilization lives on. But more numerically, more quantitatively, what does it mean exactly? So a type 1 cosmological civilization uses about 2 in 10 to the 17 watts. Okay, so I will give you an example now to understand a little bit more what this means, but 2 in 10 to the 17 watts means 2 followed by 17 zeros watts. Imagine that now a typical LED bulb uses probably 5 watts, and earlier incandescent bulbs used probably 60 or 100 watts. So we're talking about a huge amount of energy consumption here. Such a huge energy consumption equals about 25 million nuclear power plants. So type 1 civilization would use the energy equivalent, the power equivalent, to better say, of 25 million nuclear power plants. A type 2 civilization would use about 4 in 10 to the 36 watts and 26 watts. And this would equal to 50 million billions nuclear power plants. So we're talking about literally astronomical numbers here. To go to the type 3 civilization, which would use about 4 in 10 to the 37 watts, so again 4 followed by 37 zeros, and this equals 5 billions nuclear power plants. So the energy production at every second of all the stars in our galaxy. So you might be questioning yourself now, at what kind of type is our civilization right now? Well, not even one. So you can make a little calculation, assuming an energy increase by our civilization of about 3% per year, like it's been happening in the last 10 or 20 years. And you would calculate that our civilization would reach a type 1 on the Kardashev scale in about 100 years. A type 2 in about 5,000 years, if we're still here, and most unlikely, maybe a type 3 in 1 million years. So now the problem is, a type 3 civilization would use so much energy that we would be able to know actually if there is any civilization of that type out there, at least in the local universe, because this civilization would produce a huge amount of energy, and our telescopes would actually be able to detect this civilization. Well, unfortunately, there is no evidence of a Type 3 civilization, at least in the local universe, meaning in the nearby galaxies. And this was a paper in 2015 that analyzed the signature, the thermal signature that an hypothetical Type 3 civilization would produce. And in no galaxy, at least in the local universe, there is any of these signatures. So no Type 3 civilization so far. But the question is, how are we going to produce so much energy? I mean, it's a huge amount of energy. So let's see a little bit what are the types of energy, or at least the energy sources that are out there in the universe. Well, the first one is very easy. It's our sun. So this is a video that was taken by a NASA spacecraft, the SDO, the Solar Dynamics Observatory, and you see that the sun is an incredible is producing an incredible amount of energy every single second in the past billions of years. So you see protuberances, explosions on the sun. And the sun is able to produce about 4 × 10⁻26 watts, which would put us on a Type 2 civilization. So if we were able to use all the energy produced by the sun, we would be automatically on a Type 2 civilization. There is another very, very peculiar and powerful energy source out there, and these are supernovas. Supernovas are stellar explosions. This is a simulation, of course. It wouldn't be so beautiful in a real telescope. So these are very massive stars, talking about tens of times more massive than our sun. And when the nuclear fuel that is powering this star terminates, it ends, so the star collapses and then explodes, like you can see in this simulation. And the power that is generated by a supernova is about 5 × 10⁻36 watts. So this would put us almost on the brink of reaching a Type 3 civilization. But the problem is that, as you can see from this video that is repeating many, many times, supernovas are very short events. They last about 100 seconds or even less. So all this incredible amount of energy is produced in just a fraction of time, so a very short time. So unless we have any means of collecting this energy, we can't really use a supernova to power our future and perspective civilization. So now we reach the final object that is able to produce a large amount of energy, which is my specialty. And these are supermassive black holes. And this will occupy the remaining 18 minutes of our talk. So this is a simulation, of course. We can't really see a black hole like this for the reasons that I will tell you later on. But a black hole, a supermassive black hole like the one that is depicted in this video, is able to produce about 2 × 41 watts. So this is about 10 to the 4, so 10,000 times more than needed to put us in a Type 3 civilization. So if we were able to use the energy that is produced every second by a supermassive black hole, then we would be able to literally expand throughout the galaxy, because we would have so much energy that our spaceships and everything that comes with our needs can be met. So just imagine that there is a supermassive black hole at the center of our own galaxy. So this is not literally impossible. So the question is, what is a black hole and why such an efficient way of producing energy? And so black holes, of course, deal with gravity. It's a history of gravity. And with all the history of gravities, we need to start with an apple. And I bought an apple this morning at a supermarket here in Bozen, and the cashier was looking at me a little weird because I bought just one apple, and it was 0.38 euros, and I paid with a credit card because it's the only thing that I had. So it was a pretty interesting adventure. So this is an apple, and we don't know if the history of Isaac Newton is really... Wait. Oh, sorry. Oh, no. Wait, let me go back. Yes. So we don't know if the history of Isaac Newton is really true, but we have our common experience that if we take an apple or literally any object and we throw it into the sky like this, the apple falls back. You've never seen an apple that never comes back onto the ground, right? And this is true for any object, of course. Now, the problem is that if I were able to launch this apple so fast to reach about 11.2 kilometers per second, which is the escape velocity from our planet, this apple would never come back, would just go into orbit and then leave the gravitational field of our planet. So is it possible at all to build machines that accelerate apples or payloads or satellites to the escape velocity? Of course it's possible, and we see it at every rocket launch. There was a rocket launch yesterday, I think. The TGs also talked about that. And this is the launch of New Horizon, a satellite, a NASA satellite that was launched about 10, 15 years ago, I think, to Pluto, the farthest planet in our solar system. And of course, to reach Pluto, the satellite needed to be accelerated to the escape speed of our planet. So what is that escape speed? The escape speed from our planet is 11.2 kilometers per second, or about 40,000 kilometers per hour. So one important aspect of the escape speed or the escape velocity is that it increases with mass. Okay, so if you take Jupiter, it is the most massive planet in our solar system. The escape velocity is actually higher. It's about 60 kilometers per second, or about 214,000 kilometers per hour. So remember, if you increase the mass of an object, or a planet, or a star, whatever you want, or if you decrease its size, so you shrink it, then the escape velocity increases. And this is exactly what a black hole is. A black hole is a body, an object, whatever you want, that is so massive and so compact that its escape velocity, so this escape velocity here, is higher than the speed of light, so 300,000 kilometers per second. Now, the structure of a black hole is very simple in reality, and I will describe it a little bit more later. So the black hole itself is really a singularity, so it's a point in space of infinite density in principle, and what we usually call the dimension of a black hole, so how big it is the event horizon. Now, be careful, an event horizon is nothing that you can touch. So it's not a real surface, it's just a mathematical surface. And the event horizon is where the escape speed equals the speed of light. What does it mean? It just means that if there is a ray of light inside the event horizon, it cannot escape. So it can't reach us anymore. Instead, if there is a ray of light there is outside, even slightly outside the event horizon, then in principle, this ray of light can reach us. Now, I do black holes in my life, so I'm in love with black holes to some extent, but there is a property of black holes that is very, very interesting also for the general public. And it's related to how you describe black holes, okay? If you want to describe a person to a friend, you need to use a long list of properties, right? You need to use the color of the hair, how tall she is, what she's wearing, for example. But for the black hole, for any black hole, an identity card of a black hole, this is an Italian identity card, of course, consists of only 3 properties. So you can see them in segni particolari. So a black hole can be completely described by only 3 properties. So that are the mass, the spin, so how fast it's rotating around its own axis, and the charge, the electric charge. But in reality, most of the black holes are electrically neutral, so there is no charge. So in practice, only the mass and the spin can be used to completely describe a black hole, at least in mathematical terms. So today I won't be speaking about the spin because it's a little bit more complicated and we don't have time, but to really understand the energetics of black holes, so why they produce energy, it's very important to talk about the mass. And it's also the main parameter. So the mass determines the dimension of a black hole, so how big it is, at least the event horizon, and the category, if it's a small black hole, a very big black hole, etc. So I'll make a little example so to understand how compact and how dense a black hole is. Take the sun. Our star is about 1.4 million kilometers in diameter. And if the sun were to collapse into a black hole, spoiler, it won't happen, no worries, but if it were to collapse into a black hole, it would occupy a sphere that is about 1.3 kilometers in diameter, so not even the diameter of Rome. You see, St. Peter is not even included. So if you collapse our sun to a sphere of 3.1 kilometers, that would be a black hole, okay? So you might imagine at this point, okay, black holes are small. Not really. No, they're not small at all. In this example, it's small, but there are black holes that are much more massive than this. And the most massive black hole that we have discovered so far, it's a black hole that is inside this galaxy. So what you see here is a galaxy, and the black hole that the heaviest black hole that we've discovered so far is at the center of the galaxy. So it's partially the light that you see at the center there. So how big is this black hole? How massive is it? It's about 17 billion times the mass of the sun. So if you take our sun and you take another 17 billion times its mass, then you can construct this monster in the universe. So how big is it in dimension like? So this black hole that is inside NGC's 1277, it's a galaxy, is so big that it is about 15 times the size of our own solar system. Okay, so this is the orbit of Neptune, the little blue circle that you see here. So you take about 15 times, 10, 15 times approximately that size, and you get the dimension of this black hole. Okay, so just let that sink in. We are talking about a single object, not a collection of objects. This is a single object that is 10, 15 times bigger than our own solar system, which is composed of many, many objects, as everybody knows. So this is a family portrait of black holes, just to describe a little bit how big they are. So on the left side, you see stellar mass black holes. These are classic black holes. They are up to 100 solar masses, and there is a bunch of them everywhere in our galaxy, and in any galaxy, to be true. And there are about 100 million of these objects in our own galaxy, but again, don't worry, they are not going to come right now. We don't know. It might happen, actually. But don't worry too much. And on the right side, you have supermassive black holes. These are black holes that are above 1 million times the mass of our sun. And they usually sit at the center of galaxies for the reasons that I will tell you at the very end of this presentation. So to go from stellar mass black holes to supermassive black holes, this process takes a very, very long time. And we won't go into these details today, but you can ask me later if you want. So in the last 7 minutes, I want to talk about the energetics of black holes, which is the most important point here, because this is the Futurological Congress about energy, after all. So you might be asking yourself, how can we observe black holes? I said before that nothing, not even light, can escape the gravitational field of a black hole. So how are we going to observe them if they don't emit light? Well, they emit light, but in a way that it's not really obvious to understand. This is a black hole. Okay, this is not a galaxy. Most of the light that you can see here comes from the black hole itself, and it's 3C273, the first quasar or supermassive black hole that was discovered in 1963. So when astronomers discovered this object and they calculated how far it is, they were astonished. They were astonished because this object is extremely bright, so we can see it, that it's really bright, but from their calculation, it was too far to be so bright. Okay, so how is this object producing so much energy that is very far away, billions of light years, and is still so bright to be so visible from our telescopes? Well, this is exactly the point. So black holes are the most paradoxical objects that you will find in nature. So you remember that at the beginning I showed you just part of this illustration, just the central part here with the event horizon. And it's absolutely true, I didn't lie to you, that black holes don't emit light from the event horizon, so from the black hole itself. But it's also true that the space around black holes can be extremely bright. Actually, they can be the brightest objects in the entire universe. So how does it happen? It happens because the accretion disk, so all the material that is falling into the black hole, becomes so hot, and we're talking about millions and millions of degrees of temperature, that they start to shine. As you can imagine, the gas in our kitchen that becomes very hot, and it starts to emit light on its own. So to better understand this, in just 1 minute, I will go back to our apple example. And we go back to Newton. So let's imagine that we have an apple here on the tree, and this apple is in the gravitational field of our planet, so it has some gravitational potential energy. So gravitational because there is a gravitational field out there, potential because it's not really happening yet. The apple is still hanging from the tree. So once it starts to fall, that energy goes from potential energy to actual energy of some other sort. So what happens exactly? Let's imagine that we release the apple from the tree, and I will do it also in real time here. What happens is that this apple starts to accelerate to the ground, and the gravitational potential energy transforms into kinetic energy. And once it hits the ground, this kinetic energy gets dissipated. It gets dissipated in heat, gets dissipated in sound. So what happens if I actually do this? Right? So what happened is that the apple went down, it touched the ground. The little spot where this apple impacted actually got a little bit heated up. We can't really see it, but it happened. And also the rest of the energy was dissipated via sound. You heard it. So this is exactly what happens in black holes. So let's imagine that we have an apple, again, because we love apples, and it's going towards a black hole. So what happens is that there is a gravitational potential energy at the beginning, and if you don't like apples, you can put a spaceship there, an asteroid, a planet, whatever. And what happens is that then it accelerates to the black hole, and that's transformed into kinetic energy. It reaches the accretion disk, and in the accretion disk, there is energy dissipation. So all the kinetic energy gets transformed into heat, gets transformed into radiation, ultimately, because the matter is very, very hot. So this is how and why black holes are so efficient energetically, because they transform matter directly into energy by dissipation. So this is a more detailed picture of what happens in a black hole. This is a simulation by a friend of mine, Andrew Chale, in Princeton. So this is the black hole at the center here, the little black square, black circle. On the right part of this simulation here, you see that there is gas falling onto the black hole. And at the other side, so on the left, especially the top left, you see radiation, so the simulation of radiation that gets emitted. So, and also magnetic energy on the bottom. So what happens is that whenever matter falls into a black hole, energy and other radiation and any other energy gets emitted by the black hole. So in the last couple of minutes, I want to talk how efficient are black holes compared to terrestrial, to terrestrial examples that we know of. So the conversion efficiency that we're talking about at this point is the matter to energy conversion efficiency. So imagine that you have a little rock of whatever mass you want. The question is how much of this mass can be transformed directly into energy. Well, for nuclear fission, so the process that drives our nuclear power plants, this efficiency is very low. It's about 0.08%. And it goes a little bit better with nuclear fusion, so what drives the energy in our sun and in general the stars, which is about 0.7%. And now with black holes, so with a static non-rotating black hole, the efficiency is about 6%. So we're talking about 100 times more efficient than our nuclear power plants. And just imagine for rapidly spinning black holes, the efficiency can reach 32%. So about 1/3 of the mass of the initial rockets gets completely transformed into energy by the spinning black hole. Now, my time is up, but I wanted just another minute to conclude this presentation, just to make you understand why is it so important to study black holes. We don't expect to use them to produce energy in the near future, at least, because it's very complicated. But why are they important? They are important because they co-evolved with galaxies, though there is a very important connection with galaxies. So in the universe, we have small galaxies, we have big galaxies, and we also have big black holes and small black holes. Now, these are not ordered randomly, but they are ordered in such a way that big galaxies are hosting big black holes and small galaxies are hosting small black holes. For example, our own Milky Way has a black hole of a few million solar masses, and M87 and is much bigger than the Milky Way and has a black hole that is billions of solar masses. So black holes are very important because they drove the stellar evolution of a galaxy. So to some extent, they co-evolved with each other. So finally, why are galaxies important at this point? So you all know the moon, our beautiful satellite, and you know, it occupies a very small patch into the sky. This is a picture that reveals how small it is in the sky, and this is a zoom in of our moon. So just imagine to take a picture of the sky, so of the deep sky, that is so small. So it's about 1/10 of the diameter of the moon. Of course, you can't take this picture with your iPhone, but you need a Hubble Space Telescope to do that. And if you take an ultra-deep picture of such a small patch in the sky, this is what you get. This is the Hubble Ultra Deep Field, and all the points that you see there, they are not stars, they are galaxies. So there are about 10,000 galaxies just in this little spot in the universe. So my final message is that black holes are very important for the evolution and the formation of galaxies, and galaxies are important because they are the building blocks of our own universe. Thank you.